Good morning, Chemistry 1 students. Here are your Chapter 15 Day 1 notes. You should have your Chapter 15 outline out and in front of you. We are going to begin at Section 1, Electron Configuration in Ionic Bonding, and we are going to go through and finish the octet rule. So you've sort of been introduced a little bit to ions. In Chapter 14, we talked a little bit about the fact that you form an ion by either gaining or losing electrons. Remember, we form ions by gaining or losing electrons because our other choices besides electrons would be protons. But if we gain or lose protons, we change the atom because that's changing the atomic number. So we can't gain or lose protons. We also can't gain or lose neutrons for a couple reasons. Reason number one, right? Changing the number of neutrons. Neutrons are neutral. That would in effect making it an ion. Number two, changing the number of neutrons. Remember, that's what isotopes are. So the only way that we can form ions is by gaining or losing electrons. So we have to talk about those electrons. So we're going to start by talking about what are called valence electrons. And you need to know that all the elements within each group of the periodic table react in similar ways because they have the same number of valence electrons. So the reason that atoms that are in the same group of the periodic table behave the same way chemically is because they have the same number of valence electrons in their atoms. The definition of valence electrons are the electrons in the highest occupied energy level. Remember, we've abbreviated this before, the HOEL of an element's atoms. So these are the electrons that are on the outside of the atom. And the number of valence electrons, which again I gave you kind of an abbreviation because we're going to refer to valence electrons a lot between now and the end of the trimester. So the number of valence electrons largely determines the chemical properties of an element. So pretty much all of the chemistry of a particular element or atom is because of the number of valence electrons it has. So we need to know how to figure that out. So determining the number of valence electrons. And again, it's going to be helpful to be looking at your periodic table. The number of valence electrons is related to the element's group number in the periodic table. So, how do we use our periodic table to determine the number of valence electrons? To find the number of valence electrons, an atom of a representative element. Remember, by representative element, we're talking about the tall columns on the periodic table. You simply look at its group number. So, what I'm talking about here are group 1A, 3A, 4A, 5A, 6A, 7A, 8A. Those group numbers, and 2A, sorry, that are on your periodic table for the tall columns. Okay, so you're going to look at that group number. That group number is telling you the number of valence electrons. So group 2A has 2 valence electrons. Group 5A has 5 valence electrons. Okay, that's why those designations are nicer than some other way they're designated. So, for example, group 1A have 1 valence electron. Group 4A have 4 valence electrons. Group 6A have 6 valence electrons. Group 8A, the noble gases, are the only exception, and there's really just one exception, because helium only has 2 valence electrons. And remember, that's because helium is in the first period of the periodic table where you're in the first energy level. You only can have one sublevel, which is the S sublevel, which only has one orbital that holds 2 electrons. Okay? All the rest have 8 valence electrons. And it is usually only the valence electrons involved in chemical bonds. Therefore, okay, we only show valence electrons in our electron dot structures. So because it's only the valence electrons that are involved in forming chemical bonds, okay, as we start to look at these electron dot structures, the only electrons we're going to show are those valence electrons. An electron dot structure is a diagram that shows valence electrons in the atoms of an element as dots. The dots should be placed individually before being paired up so that just means we're going to kind of put one dot on each side of our symbol before we start to double them up. And these dots that are our electrons represent the S and P electrons. So we're representing the electrons in the S sublevel and the P sublevel. Remember, S sublevel has one orbital and it holds 2 electrons. The P sublevel has 3 orbitals, each holding 2 electrons, so that's 6 more. So the maximum number of dots we're going to have are 8 dots. So some practice writing these. For number 1, we're going to do aluminum. If you would start by going ahead and writing the electron configuration, and let's make it the complete electronic configuration for aluminum. That means like the superscripts, right? So the electron configuration of aluminum, we start at the top left-hand corner. We have 1s2, 2s2, 2p6, 3s2, 3p1. Now, we're only representing the electrons in that highest occupied energy level. So our highest occupied energy level are the 3s1 and the 3p1 in aluminum. So we write the symbol for aluminum. Our symbol represents, okay, all of that electron configuration. Okay, so it's representing all of those interior electrons that aren't on the outside. So aluminum should have a total of 3 dots, 2 S's and 1 for the P. You also can tell that from the periodic table because remember it's in group 3A, and group 3A has 3 valence electrons. So we put a dot, we kind of imagine that aluminum is 4-sided, so we put 1 dot on each side of aluminum, and it doesn't matter what side you choose. So that's the electron dot structure for aluminum. Let's take a look at a second one. Let's take a look at oxygen. Again, if you would pause this for a moment and go ahead and write the electron configuration for oxygen, just like we just did for aluminum. So we start at our upper left and we have 1s2, 2s2, 2p4. Again, that highest occupied energy level portion, that's the 2s2, the 2p4. So my symbol O, again, remember that's representing all of that. And now I'm going to put 4 dots. So 1, 2, 3, 4. I put 1 dot on each side of oxygen. Oh, sorry, but I'm supposed to have 6. So there's my 4. Here's 5. And here's 6. And again, it doesn't matter where you put the paired up ones. Okay. Now, I don't have to write my electron configuration for oxygen if I don't want to. You can look at your periodic table and look at the fact that oxygen is in group 6A, so that means it has 6 valence electrons, and so I need to put 6 dots around oxygen. Lastly, we're going to look at argon. Again, we're going to write the complete electron configuration of argon, which is 1s2, 2s2, 2p6, 3s2, 3p6. Again, the part of this that is the highest occupied energy level, that outermost shell, is the 3s2, 3p6. So notice again we have 8 valence electrons, which we could just look at our periodic table and see that argon is in the noble gas, or group 8A, and so it has 8 valence electrons. So we write our symbol for argon: 1, 2, 3, 4, 5, 6, 7, 8. There are our 8 dots. There is our electron dot structure for argon. Again, this is important because the electrons that are involved in forming chemical bonds are always going to be the electrons in this highest occupied energy level, or these valence electrons. So let's take a look at the electron configuration for the cations. We have a rule that applies not just for cations but also for anions, and it's the octet rule. And the octet rule states that in forming compounds, atoms tend to achieve the electron configuration of a noble gas. Right? That goes back to that ChemQuest that we did yesterday, where every single time we were asking how many electrons do we have to lose to become a noble gas, how many electrons do we have to gain to become a noble gas. Because of the octet rule, every element on the periodic table is gaining and losing electrons. It's forming compounds in an effort to get the electron configuration of a noble gas. Gilbert Lewis in 1916 came up with this rule to explain why atoms form certain kinds of ions and molecules. Right? An octopus has 8 legs. An octet is a set of 8. So specifically, the octet rule is saying that there are 8 electrons in the highest occupied energy level, and the electron configuration is NS2NP6, where N right, is that principal quantum number. It corresponds to what period you're in, right? Those n's are over on the left-hand side of your periodic table, starting at the top of the periodic table with n equals 1 and going down. We know that the atoms of the metals tend to lose valence electrons, leaving a complete octet in the next lowest energy level. So we're talking about here forming cations. And this is something that's kind of nice to look at using those Bohr diagrams. So we'll just pick kind of a simple one. We will pick sodium. Sodium has 11 protons, which means it has 11 electrons. So 2 in its first, 8, 5, 6, 7, 8 in its second, and that leaves 1 electron in its third energy level. So that's sodium as an atom. Now, when sodium forms an ion, it would have two choices. It could lose its 1 valence electron to become like neon, or it could gain 7 valence electrons to be like argon. It's always going to do whatever's smaller, right? So it's going to lose 1 valence electron. So sodium as an ion, okay, is still going to have 11 protons, and it's still going to have 2 electrons in its first energy level. But now 3, 4, 5, 6, 7, 8. Now it has 10 electrons total. So this is sodium's Bohr diagram when it's a sodium ion. Notice we still have a complete octet, but, right, sodium here had 1, 2, 3 energy levels. Now sodium as an ion has 1, 2 energy levels. And it has a complete octet in the next lowest energy level, right? Because sodium had 3, now its complete octet is in its second. We would write its charge as a +1. Okay, so that's what we mean by saying that the atoms of the metals tend to lose valence electrons, leaving a complete octet in the next lowest energy level. And these are cations. Remember, in a cation, we have the number of protons is greater than the number of electrons. So that's what the metals tend to do. Okay. The atoms of the nonmetals tend to gain electrons or share electrons with another nonmetal to achieve an octet. We're going to kind of focus on the gaining part right now. We will eventually talk about the sharing, but right now we're going to focus on that gaining. So again, let's pick a pretty simple nonmetal. Let's go ahead and do fluorine. Fluorine has 9 protons. So it has 2 electrons in its first energy level, and it's going to have 7 more in its second. So this is fluorine as an atom. Now, fluorine has, right, 2 choices. It can gain 1 electron to become like neon, or it can lose 7 electrons to become like helium. It's always going to do whatever's smaller, so it's going to gain 1 electron to be like neon. So fluorine as an ion still has to have 9 protons because that is what makes it fluorine. Still going to have 2 electrons in its first. Now it's gained 1, right? It had 7. Now it's going to have 8 electrons in its valence shell. It has 8 valence electrons, right? We would write its charge as -1. So again, we have achieved that octet. This time notice, right? Fluorine as an atom had 1, 2 energy levels. Fluorine as an ion still just has 1, 2 energy levels. Okay, so we've completely filled the energy level that was only partially filled in our atom. So that is where we are going to stop for today. You do not have any homework, so it's a good day to make sure that you're completely caught up in my class and other classes. Have a good day. Talk to you tomorrow.